Good morning. First, I'd like to thank the organizers for inviting me to speak and tell you a little bit of a story about swimming in complex fluids. I've been looking forward to this week for quite some time. It just looks like it's going to be a fantastic group of talks. So, like I said, today, a story about swimming in viscoelastic fluids or complex fluids, one of many, many complex fluids. And to kick us off, I'd like to start by reminding you, maybe, of some striking viscoelastic fluid phenomena. The first is so-called rod climbing, or the Weissenberg effect. If we take a rod and it is rotating with a fixed rotation rate in a Newtonian fluid, the development of centrifugal forces will lead to the depression of a free surface near the rod. However, in a viscoelastic fluid, we find one of the first classical striking effects, which is rod climbing. So a way to understand this physically is that if we picture the complex fluid being built on a solvent into which a large number of long chain molecules or polymers are embedded, we have in this case very clearly circular streamlines, and along those circular streamlines these long chain polymers are going to stretch and elongate, and as a consequence there's going to be entropic elastic forces that are driving them back to equilibrium and a corresponding radially inward force, which, again, in the presence of a free surface, is going to lead to a strangulation effect. Okay? Another wonderful recent, maybe not so recent now, investigation has been into phenomena such as mixing. So mixing is generally a very, very hard thing to do with zero Reynolds number. However, if we simply, Grossman and Steinberg, Thomas and Shelley-Hifo, and others, just look at a periodic 4-roll mill that they set up in a Stokes and viscoelastic flow, they find that the onset of large-scale, unsteady and chaotic structures can be developed. So that's a very intriguing direction for the consequences of viscoelasticity at still very, very small Reynolds numbers. Another experiment that you can do even now if you're discrete is to look at beads on a string. This is a phenomena that occurs if you have a very thin cylinder of viscoelastic fluid. And in fact, what you'll see is that there's the viscoelastic effect enhances the growth of these beads, and it also delays the pinch-off, which means that you can see these beads on a string in your, for instance, saliva, which can be quite viscoelastic at the right scales, and they can persist for quite some time. So I've been thinking about locomotion in complex fluids. Complex fluids, of course, being a very, very large umbrella. Very many models, very many types of fluids, very different types of dynamics, viscoelasticity, shear thinning, shear thickening, etc. But I'd like to introduce you to a puzzle. And it's going to take a number of slides to develop this puzzle, but you'll see just by some of the previous works that have been done in this field, you'll start to get a sense of the nature of the puzzle. So again, biological fluids are, of course, frequently non-Newtonian, very complex. Think about swimming through mucus as an example of a very complex inhomogeneous fluid with multiple relaxation timescales, etc. And so we can think about having a very complicated polymeric microstructure. And if there is a fluid flow, then in general there are going to be viscous stresses that are competing with the entropic contraction of polymers and corresponding elastic stresses. So as two examples, these are two helical bacteria, Leptospira and B. bergdorferi. They are well known because they will lead to leptospirosis and Lyme disease and a host of other problems for humans. So of course, they find the money. And what's observed in experiments is that these helical organisms will actually locomote faster when the fluid exhibits viscoelasticity than they would in a Newtonian fluid of the same viscosity. Meanwhile, other experiments on C. elegans, which is a nematode and that undulates using planar waves to swim along of a very small wave number, maybe a half. These are experiments by Shen and Araccia. Here's the swimming speed relative to the Newtonian swimming speed as they change the Deborah number, which I will introduce in a moment. And their experimental data are shown in squares, and they find that with the introduction of viscoelasticity, the body swims slower. Okay, so helical bodies seem to swim faster, maybe? Planar waves slower? Is it finite amplitude, finite body? What's going on? And of course, more complex phenomena abound because this is biology we're talking about. So if the body itself is, for instance, elastic or deformable, the amplitude and the wavelength of spermatozoa, for instance, decrease with the onset of viscoelasticity. Now, the amplitude and wavelength decreases is going to lead to straighter swimming paths, but they actually swim slower in general. However, hyperactivated spermatozoa, which are very large amplitude, it's a different phenotype for this organism, they actually swim faster than in a Newtonian fluid. So again, the plot is thickening. We're seeing that it may just be a very complicated question about geometry and nature of propulsion, but even more complex phenomena exist, such as the Heliobacter pylori, which changes the pH of the mucus in your gut in order to reduce the viscoelastic network into a sol phase in order to swim through in a more Newtonian style. So as a starting point for modeling, there are of course many models for complex fluids, but a commonly investigated one in Locomotion is the Oldroyd B model. So I'm going to present the Oldroyd B model. It's a model that has viscoelastic effects, but it has no shear thinning and no shear thickening. It also has one relaxation timescale. So it is in one sense a very simple model. It's sufficiently complex to give us some headaches, but it at least isolates the effects of viscoelasticity, which I think is of value. So to begin, of course, we have the momentum balance equation of Cauchy, where we have the gradient of the pressure is balanced by the divergence of the deviatoric stress tensor. And mass conservation comes in the form of divergence of the velocity field is 0. Now, the deviatoric stress is written as a linear composition of the solvent stress and the polymeric stress. So here I have my flow field with velocity u. And to split these up, first we have that the solvent stress is going to behave following the general Newtonian law, constitutive law, which is a linear relationship between stresses and strains. So eta sub s is the solvent viscosity, and gamma dot is the symmetric rate of strain tensor. Meanwhile, the polymeric part of the stress is going to satisfy a so-called Maxwell model, which if you'd like to think about this in one dimension, you can think of two beads connected by both a spring and a dashpot in series. So there is going to be some kind of an elastic modulus and also a viscosity associated with the damping of this particular model. This leads to a relaxation time, lambda 1. So in this Maxwell model, this triangle here, it's a time derivative, which I'll say more about in just a moment. Well, let's say more about it now. It is the so-called upper convective time derivative. So it looks like a material derivative, plus there are some extra terms here, some nonlinear business. And what this is basically it's just a way of capturing the transport not only of the frame, but also the deformation and rotation of the basis vectors as you're moving through the fluid. Now, there's a more general, for instance, Gordon-Showalter derivative, which is another objective time derivative, but it introduces another parameter. So again, for the sake of simplifying things, we're going to start with the upper convective Maxwell model. So in 3 dimensions, that time derivative, again, looks like this more complicated upper convective derivative. But you can think just physically about a multi-connected bead spring model, which has entropic relaxation and gives rise to 3-dimensional elastic relaxation and damping forces. Eventually, I'm going to start talking about helical bodies in a viscoelastic fluid. So just to get our dimensionless numbers worked out, let's talk about non-dimensionalization for just a moment. I'm going to take a helical body eventually, which will be rotating with a fixed rotation rate omega, and the wavelength is given by 2 pi alpha over k. So k is a wave number and alpha is a pitch. So by scaling the lengths on the wavelength, time on the rotation rate, and velocities on their ratio, then, and finally stresses on the total viscosity, which is the sum of the solvent and polymeric viscosities, we'll end up with the dimensionless constitutive law. So we have that the total deviatoric stress is related to the symmetric rate of strain tensor with 2 important dimensionless quantities showing up. Well, first we have the viscosity ratio of the solvent to total viscosity, and we also have the Deborah number. The Deborah number is a comparison between the time scales associated with the rotation of the filament and the relaxation time scale of the elastic fluid. And I should also say that we have two other dimensionless quantities swimming around based on the geometry. So having made the system dimensionless, we'll still have that the pitch of one wavelength is alpha. So this distance is going to be 2 pi alpha. We'll have a tangent angle everywhere psi, and now a helical radius of beta and a filament radius of big A. So that's just two other quantities because, okay, we'll generally have to think about the filament thickness A, but beta, alpha, and psi are all related to each other in a relatively simple manner. So generally I'm going to talk about the pitch angle and the helical radius. So the wave speed, for instance, if I rotate this thing around, we've made the system dimensionless on the rotation rate, so that's just going to happen in unit time, which means that the wave speed of this body moving downward is going to be alpha. And a brief and free historical notes for those of you who have not yet seen this, maybe only a few of you out there. But the name Deborah number, unlike many of our dimensionless numbers, does not come from the name of a particular scientist. It was proposed as a name by Marcus Reiner, who was at the Technion early in the 20th century, and it was named after a passage in the Book of Judges called the Song of Deborah. And the Song of Deborah stated that the mountains flowed before the Lord. And so the idea is that in order to understand the nature of deformation and flow, really it's important to have a characteristic timescale in mind. So on geological timescales, maybe the mountains will be flowing along. Interesting guy also coined the term rheology with Bingham. That rheology is a study of deformation and flow of matter. This was inspired by the aphorism of Simplicius, which is Panta re, everything flows. Okay. So I've given this talk a number of times, and some people would like me to present the work in terms of another dimensionless number called the Weissenberg number, which has a less interesting backstory. But in that case, what we're doing is we're comparing the elastic relaxation timescale to a timescale associated with the shear rate. So if I think about a cylinder and moving with some fixed velocity, the cylinder might have a radius A, then we'll be comparing a representative timescale U over A to lambda 1. But in the case of a helical body, we can think about, since it's not going to be swimming very fast, you can think about planar motions in 2 dimensions, and the cross-sectional velocity that you would take then would just be the helical radius B times the rotation rate. And so that means that the Weissenberg number, in my particular case, is going to be simply the Deborah number times some prefactor, which is geometry dependent. And given our non-dimensionalization, it's just this beta over A. So, but the point is that everything I'm going to say here is going to be in terms of the Deborah number, but if you prefer the Weissenberg number, it's a very, very simple translation. You can think about what I say as a proxy for the Weissenberg number. Okay. So I wanted to present the old rate B model early on so I could talk about the Deborah number, but now I want to go backwards and think about some of the previous work that's been done in swimming in general and in swimming in viscoelastic media. Since we're here, let's start with the classical work of Taylor in 1951, who had one of the earlier papers on the swimming of microorganisms in general. So he has an infinite 2-dimensional sheet on which a prescribed waveform is passed. The waveform is small amplitude relative to the wavelength. So if it's passing waves with a speed c, it turns out to the left with speed u sub n. That's for Newtonian speed. He solves the Stokes equations by defining a stream function. We're in 2 dimensions. So psi is a stream function. We have a biharmonic equation for psi. And the trick then is to use a small amplitude asymptotic. So epsilon's a small number. It's, again, the amplitude divided by the wave number, or wavelength. So then it's a simple pedestrian asymptotic expansion to find equations for psi 1, psi 2, and so forth. And you find, for starters, note that the swimming speed at leading order has to be 0. And that's just, you can see this by symmetry. If we're expanding the velocity, the swimming speed as epsilon u1 plus epsilon squared u2. If we take epsilon to minus epsilon, we're just simply translating the sheet by a half period. So nothing can happen, in other words. So at leading order, it must be the case that the swimming speed is second order in the amplitude. That's a classical result. And in particular, the Newtonian swimming speed normalized by the wave speed is given by 1/2 bk squared. So squared in the amplitude. And corrections at fourth order. Now, one of the very well-cited recent works on swimming in a viscoelastic fluid was given by Loga in 2007, who did precisely the same problem, but in a host of different types of viscoelastic fluid models. And so the difference is that he would solve, for instance, he started by solving the Stokes-Oldroyd B system, but now he has an asymptotic expansion in the stress as well, in powers of small epsilon, or amplitude. And what he finds is very interesting, is that the swimming speed in a viscoelastic fluid, normalized by the Newtonian speed, is given by this ratio, sometimes now called the Loga ratio. But we see our two interesting dimensionless quantities for the fluid here. We have that the solvent viscosity divided by the total viscosity. Of course, that's bounded by 1. And we see the Deborah number. So as Deborah number goes to 0, you're swimming in a Newtonian fluid. But for non-zero Deborah number, since this is bounded by 1, it always swims slower. So the two-dimensional small amplitude swimming sheet always swims slower in a viscoelastic fluid. He performed similar computations for other models like Feeney-P, finite extensional nonlinear elasticity, in which these polymers end up having a nonlinear. They can support large stresses or extensions with stress increasing. Johnson, Siegelman, Oldroyd, and Giusekis, there are other models that include that Gordon-Showalter derivative and things like this. But the point is that at the leading order, he finds that the swimming speeds all have exactly this form. So the idea is that even though we're using the Oldroyd B model, at least in this particular calculation, it ends up not being so important. That the idea is that swimming in a viscoelastic fluid should lead to slower swimming, which maybe is part of the puzzle here, because we've seen some observations already that it's possible to swim faster. Is it that it's a planar wave? Is that why C. elegans swims slower? Is it because it's of infinite extent here? There's no pitching? What's going on? Just a side note for the experts in the room, the swimming speed is determined at second order in the amplitude here, which means that you have to keep the nonlinear terms in order to understand what is the effect of viscoelasticity on the swimming speed. So we're going to see a recent paper where that's not the case in just a moment, but that's just a side note. Not much longer, Fu, Powers, and Wolgemuth, or Fu, Wolgemuth, and Powers, studied a very similar problem where they had a helical body, and it was either transmitting planar waves or helical waves down along its length. But it was, again, a very small pitch-angled helical body of very large thickness. And so basically, if you're a little bug sitting on top of the surface with sufficiently large helical filament thickness, it more or less looks like a two-dimensional wave. And so what they find is exactly the same swimming speed or decrease in swimming speed as in the paper by Loga. And this is to be contrasted with another recent work in which Alex actually looked at a rotating helical body in a fluid that into which stationary objects were placed, and they could also be made free. But in either case, the swimming speed was found to increase monotonically and with the wave number, and I think also with the concentration density. Is that right? It's monotonic? Yes. Okay. Point is that there's a distinction to be made between just having a network and having some kind of an elastic restorative force in the fluid. Another recent work looked at the classical three-sphere swimmer, and they found, in fact, that the swimming body could move faster and with greater efficiency than a Newtonian swimmer. And that's interesting because what they did was, again, small amplitude asymptotics. But since this particular swimmer swims at leading order in the small number epsilon or amplitude, in fact, they can use just a linear viscoelastic theory, and it actually predicts what they've computed. In contrast to some previous work in the 70s by Volkberg and Cass. Okay, so I'm almost done presenting the puzzle. So far, I think the point has been that there's different things that can happen and seems to depend on the geometry. What about finite bodies? All these previous works were looking at infinite bodies, say for the three-sphere swimmer. But Karen, Fauci, and Shelley looked at a two-dimensional body of finite extent and increasing amplitude towards the tail. What they find is that at approximately Deborah number 1, there is a maximum of swimming speed and efficiency. And they point to the development of the largest distension of the polymer coils near the tail, in the localized region where the largest amplitude oscillations are being performed. And the idea is that maybe there's a storage of elastic stress in the fluid, and then on each half stroke you come back and maybe reabsorb some of that elastic energy that's been sitting around. If Deborah number 1 would be the right time scale for that kind of transmission of elastic forces. But it's still not entirely the case. Is it this end effect, or is it this increasing amplitude? Because if they don't have the increasing amplitude, they don't get this effect. It actually just swims slow. So the plot is still thick. And then finally, here's a recent experiment by Leo Powers and Breuer at Brown. And they had this great experiment where they took a helical rigid filament and they put it inside a Boger fluid, which is a commonly used fluid that exhibits viscoelasticity but no shear thinning or thickening in the regimes generally considered. So it links up with the Oldroyd B model relatively well. But what they did was, to study the free swimming problem, they would rotate the helical filament at a fixed rotation rate, and then they would draw it out of the fluid at just the right rate so that the digital balance on which the entire apparatus was placed would be zeroed out. Really inexpensive and clever way to go about their life. And what they find was, as they look across the Deborah number, which they can do by just increasing the rotation rate, is that the swimming speed relative to the Newtonian swimming speed increases, once again, to a peak in the Deborah number order 1 range, but then decreases. And they find that this effect is amplified for larger polymeric viscosities. And unfortunately, they had a signal-to-noise ratio issue if they wanted to look at small amplitude helices, which means that, okay, we now have experimental and biological observational evidence for faster swimming in viscoelastic fluids. We have theory for slower swimming of helical bodies in viscoelastic fluids, but they're small amplitude asymptotic calculations. But there's a gap there, and they couldn't do the small amplitude things in experiments, and the theory can't go to high amplitude. There's the puzzle. So that's the gap that I wanted to try to investigate. So the experiments of Leo, Powers, and Breuer indicated that regardless of the length of the filament that they chose, they would find more or less the same dynamics after maybe 2 or 3 wavelengths. So I want to study an infinitely long helix of finite, and by that I mean non-small amplitude. And I want to do the force-free swimming problem. This turns out to be hard for a lot of reasons. First, it's a fully three-dimensional problem. It's not a sphere, it's not a cylinder, so we'll call it a complex, or we'll say at least non-trivial geometry, although it certainly has a symmetry that we will exploit momentarily. And it should also be stated that in the Oldroyd B model, instabilities and exponential growth are possible. If we just have the 4-roll mill setup, we have an extensional flow. You can think about this as elongating the long-chain polymers, and this leads to rapid increases in elastic stresses and stress gradients. So there are problems both analytically and numerically. Specifically, the High-Weissenberg number problem is an issue that most people in numerical complex fluids have to face. Things generally break down for sufficiently high Weissenberg number problem, depending on the problem itself. And it's been suggested that exponential growth in stress is not balanced by convection in a lot of the usual ways of going about computations. Okay, so let's exploit the helical symmetry. That's simple enough because I'm going to assume that we are in a steady state. I just want to look at the steady state swimming speed. Okay? Now, if we're in a steady state with respect to the body frame, then if I can tell you something about one cross-sectional plane, then of course I can tell you everything about R3 because I can translate and rotate that plane. If I have velocity or stress information there, I have it everywhere. Right? So just as a very simple movie, I'm just going to show that if we study the problem in the lab frame versus a translating frame, we can get things to be quite nice and exploit Galilean invariance here. So we're just moving along into, we see in the lab frame rotation, and it's actually swimming slightly upwards, maybe you can make out. If we move down with the wave speed, we still have that the body is swimming with some swimming speed, but if we now correct with that, then if we put ourselves in just the right frame, the wave speed minus the swimming speed, then we'll get that the geometry is fixed in space. We may have a tangential slip velocity because the tangential component of velocity is, of course, smaller than the axial component of velocity. So nevertheless, what happens is that in this frame, we have that if we are in a steady state with respect to the body, that a total time derivative of any scalar quantity in this frame is 0. And what that means is that a time derivative in this frame can be written as a z derivative. So it's basically, think about a traveling wave solution. So that's nice. All of these time derivatives I have in my constitutive law I can now replace by a z derivative. And moreover, the z derivative, think about I've got a helical body. If I would like to take a z derivative by looking up somehow, well, just by this helical translation rotation, I can just look to my left or right in the plane to get the same information. So that means that z derivatives can be written as derivatives in r and theta, because I'm going to end up using a polar coordinate system in the plane. So all the t and z derivatives can be written as r and theta derivatives with maybe some prefactors, but they're only cosine and sine. It's not so bad. And so at this point, we need only solve steady PDEs in r and theta. So we reduced the three-dimensional problem down to 2D. We still have three-dimensional velocity fields and stress and so on and so forth, but we've now made the problem more or less computationally tractable. Now, the real meat of this work ends up being computational. I'm not going to spend time discussing that part of the problem, but just to give you a sense of the type of machinery that went into solving the problem. Again, in the plane, we just use a polar coordinate system so that it's body conforming, and we choose an outer radius that we eventually make so large that it doesn't affect the results. Mixed Galerkin and finite difference approach is used, so if derivatives radially are computed using fourth order finite differences, and the equations of motion are made to be satisfied both in a collocation manner, so at every radial grid point, but then also against inner products with the Fourier basis functions in the azimuthal direction. So if it's periodic, you should be using the periodicity. So it ends up being the case that we only need a couple Fourier modes sometimes, or maybe a few, to get an extremely accurate numerical method. In the interest of time, I'm just going to skip right through the numerical part, but I'm very, very happy to talk to anyone here for the week if they are interested in the details. But think about, again, steady problem, two-dimensional PDEs. I've got a very large system of nonlinear equations, but you can think about Newton's method as being the game. Newton's method on steroids, maybe. To test the code, we use, of course, an exact solution. If we have an annulus with a helical flow, so a rotation and a translation of the inner cylinder, you can very easily write down an exact solution, and this can be used to test the code. So we find the fourth order accuracy that's expected. We find that the accuracy is 10 to the minus 5%, so this ends up being a very accurate numerical method. We can compare against boundary interval computations in Stokes flow for more complicated geometries, which we do, and a general convergence study. But the point is that things look pretty good. Another thing that you can see even in the simple example is the development of the first normal stress difference. Just in the exact solution, you'll find that you have this, again, this hoop stress or radial strangulation occurring in this type of radial flow. Okay, so there are the numerics, and now we'll skip to the results, which are more fun. First thing we can do, let's compare to the small amplitude theory. So here I am choosing a very small pitch angle, pi over 40. So these are going to be small amplitude helices. I'm going to look at the swimming speed relative to the Newtonian swimming speed, and I'm going to increase the Deborah number. So Deborah number 0, of course, I have 1. With increasing Deborah number, these different lines correspond to different helical filament thicknesses. And so in the limit of large helical thickness and small pitch angle, what we're doing is we're converging onto the analytical result. And that's consistent with the theory because in the theory of Fu et al., they throw away terms that are not logarithmic in the aspect ratio. So this is a consistent result. And we can show exactly how that result departs from the theory. But the point is that for the small pitch angle, even for very slender bodies, you're swimming slower still. Okay? Another nice thing to test in the code is something that's not just an integrated quantity, but something that has a global dependence on the fluid flow and stress. And so we look at the rate of work done in the fluid, which is a spatial integral of the stress double dot product with the rate of strain tensor. And there we see also that the rate of work relative to the Newtonian rate of work is decreasing and along the same path. So it's just another test of the code, really. So what we have so far is a numerical method that seems to be quite accurate. It matches the small amplitude helical theory. It kind of extends the small amplitude helical theory because we can look at smaller filament thicknesses. And now we get to ask the question, what about larger amplitude helical pitch angles? So I'll argue that the gap is bridged. So here if we just choose to fix the filament thickness, then for small pitch angle, we see a decrease in the swimming speed. So here, the solid lines are helical waves, and the dashed lines are rigid body rotation, which adds an extra rotation around the center line. We can do both, and we do. And what happens is that as we increase the pitch angle to a large amplitude filament, we see that the swimming speed actually can, in fact, increase relative to the Newtonian swimming speed. And the effect is more pronounced for rigid body rotation. So we were very happy to see that, and then we could continue to look at the functional relations. If we looked at thinner filaments, we found that the effect was even more pronounced. And in fact, you needed a smaller pitch angle in order to enter into regimes where viscoelasticity wasn't hurting you as much, or alternatively, viscoelasticity was helping you.
Just for clarification, what's the distinction you're making between helical waves and rigid body rotation?
So a helical wave you can picture as locally at every point on the filament, the body is just moving as a rigid cylinder in that plane, which is now not going to respect a rigid body rotation along the whole filament. So the difference is
okay, so there's
one
a special
rotation.
speed then.
No, it has to do with the twist of the filament. So there's an extra twist that occurs with the helical wave versus the rigid body rotation. The effects are going to be reduced if the filament is slender and large helical radius. Then you can't really tell the difference between the two. But if it's just a long cylinder, the difference is the entire rotation in the case of rigid body rotation. People like to think about efficiency. It's not entirely clear if that's the right thing to be optimizing over. If you're a biological organism, you might think that the right efficiency would have some kind of reproduction coefficient in the numerator. Nevertheless, it's interesting to look at the useful work done in swimming relative to the amount of work done on the fluid just through dissipation. So a common measure of the efficiency, U squared over the power dissipated into the fluid, has this structure. And if we compare to the Newtonian efficiency, we see, again, a decrease in efficiency with small pitch angle helices. This is in agreement with the theory. And increases in efficiency for large amplitude helical bodies. That is somehow corroborated by the finite body exploration of Tarrant, Fauci, and Shelley, where we again see these maxima, a maximum at Deborah number order a half, 1, something like this. I'll say more about that in a minute. And interestingly, helical waves can become quite a bit more efficient. There's less work being done on the surrounding fluid because you don't have this rigid body rotation happening. So that somehow reduces the amount of dissipation in your local neighborhood. Polymer viscosity is not quite a simple amplifier, but it almost is. This is similar to the experimental evidence of Leo Powers and Breuer, who found that as they decreased the solvent viscosity relative to the total viscosity, that they'd have amplified effects. And so we more or less see that that's the case, especially for larger Deborah numbers. But it's not the case that these all have the same 0 or 1. So it is the case that with smaller polymer viscosity or concentration, you can extend this region of enhanced swimming in viscoelastic fluids. And a fun direction that I'm kind of interested in taking this problem is, again, to think about what do people usually do in swimming? You usually start by specifying the kinematics, right? Because it's the easiest thing to do. And then the next thing you might do is to allow the geometry to be dependent on the stresses. So that ends up being a nice, sometimes very different problem indeed. And then after that, maybe there's some models for activity internal to an organism or something like this. So you're starting to link up with the biology at that point. So what I've presented so far has just been the specification of the kinematics, a rotating rigid helical filament. But we can nevertheless have some insight into what might happen if the body is itself flexible. If we simply measure the total radial force, you might think about, again, these hoop stresses that would develop on a rotating cylinder. And we in fact see that increasing the Deborah number leads to an inward force or contraction. So you might imagine that if the body is itself flexible, that you will see decreases in the amplitude at least. And that seems to be related to maybe the decrease in the amplitude of the swimming spermatozoa in a viscoelastic fluid. The force, just a little thought experiment, must be 0 in a Stokes flow. You can get that by some symmetries. If you think about time reversal. Yet another fun application of time reversal symmetry of the Stokes equation. And interestingly here, though, for a small pitch angle body, there's a sufficiently large Deborah number for which you actually get an expansion. I don't quite understand that result, but it does lead to some other interesting ideas. Namely, if I had such a body and I had a large enough Deborah number, then the forces would suggest that the filament would deform until it's a larger amplitude helical body. But now you're down here, so there's contraction, which means that for the right Deborah numbers, there may actually be a stable shape that is preferred, that is neither small nor large amplitude. So that's kind of future directions. The last thing I want to talk about is some sense of what's going on. I have to say that it's pretty complicated. It's very nonlinear, non-local, three-dimensional, complex geometry phenomenon here. But just to get some ideas, let's think about the rotation here. I'm just looking at the axial direction of the fluid velocity. Okay? So since the body is rotating and slowly moving upwards, as it passes these helical waves in the opposite direction, by the no-slip condition, fluid particles near the surface are going to be, of course, dragged upwards. So they're going to have a positive fluid velocity. And as a consequence of mass conservation, we need to be shuttling some fluid down somewhere. And the geometry of where that fluid is being shuttled down is actually, especially for large helical bodies, internal to the helical filament. So what you'll see is actually a helical body of fluid surrounding, or coating maybe, the rigid body as it moves up. And meanwhile, another helical volume of fluid being shuttled down. And what that means is that external to the filament and internal, but more so on the outside of this structure, we're going to see this type of a distribution of fluid velocity, which at least gives you an idea about the direction of the stress. I'm sorry, the shear. Okay? And the direction of shear is important when thinking about viscoelastic fluids because this tells you something about the direction into which these long-chain polymers are going to be deformed and rotated, maybe. And then to have an idea about in what sense are they regenerating elastic stresses on the surrounding fluid and body. And then in addition to this, of course, you have, if I just look down onto the plane, I have that the filament is as a cross-section moving through the plane, and so I have a similar kind of shear developing in that other plane as well. So there are two different phenomena going on here, but both would indicate that the primary shear rates are being experienced on the inside and the outside of the helical filament. So the last thing I'll show you here are the mean squared polymer distensions in the fluid. So you can think about the trace of the polymeric part of the deviatoric stress, or just think about the net average stretching of these polymers in the fluid. So starting here, I'm looking at a small pitch angle helical body and a large pitch angle helical body. And I'm going to scale up the Deborah number. And so in this first case, we're going to be decreasing the swimming speed as we increase the Deborah number. And in the second case, we'll be increasing the swimming speed until we get to about Deborah number 0.6, and then decreasing again after that. That also really complicates trying to understand exactly what's going on here. Nevertheless, in both cases, we see the development of the polymer distension at the inner and outer edges of the helical body, as intuitively suggested by the Stokesian flow. But in general, what's going to happen as we increase the Deborah number is going to be a reconfiguration and reorganization of the polymeric stresses and their communication to the pressure and other aspects of the fluid flow. And one difference that we'll see is that there is a clockwise rotation of the orientation of the mean squared polymer distension in the small amplitude case, and a counterclockwise rotation of the polymer stress in the case where the body ends up swimming faster. So this is actually similar to something seen by Alex Morozov, who studied numerics of large amplitude two-dimensional planar waves. So there's something about the delay of this stress and the rotation relative to the body geometry that's actually leading to variations in how the elastic stresses are generating fluid forces. The issue, again, also may be the order of the Deborah number. The order of the Deborah number, where we see increases in swimming speed, is a half or one or somewhere in between, depending on the situation. So this is, at least to think about, that would be the right Deborah number for which you would see, for instance, your own elastic wake in the plane. So there may be this other very non-local communication of elastic stress that you're now recovering on each half period or period. That's very hand-wavy. I don't quite understand it yet, but it's the type of direction we're trying to explore. There's also some simplified modeling using Pade approximants that greatly improve certain predictions. I'm very happy to talk to you about that offline. But just to close, your take-home messages are: the small amplitude theoretical results are recovered for helical bodies in viscoelastic fluids, and there is a smooth transition to large amplitude experimental observations. So somehow I'd like to believe that we've kind of bridged the gap between the two. This work is appearing to be more or less on its way to acceptance for publication, but I'm very happy to give you a preprint should you ask for one. With that, I'm very happy to take any questions.
So in the case that the helix is rigidly rotating, particularly when its pitch is very large, the motion is approximately circular for the cross-section in a plane.
Helical waves and rigid body motion are quite similar in the case of a large helical radius. That's right.
So in that case, so for a cylinder that moves, usually for a translating cylinder, there's a region near the rare stagnation point where there's a stress boundary layer. And
yes.
Your polymer stretch plots didn't seem to. I guess I couldn't make out if you had found something similar.
I have been looking for that kind of thing desperately, I have to tell you. But it's complicated because it's not a cylinder. And in fact, I can show you plots offline of precisely how the geometry is curving through the axial direction. And at no point is it safely a cylinder, put it that way. So I'm not quite seeing the same types of stresses that you'd see at the wake of the cylinder, for instance. So that also has complicated efforts to try to think of simplified modeling for instance, drag reduction of a cylinder through viscoelastic fluid, which is well known. It seems like it should have some consequences here, and yet every effort that I've made to try to put the two together have not been successful as of yet. Maybe someone out there will show me the way this week.
The increase of the swimming speed in your model, with the polymeric model, is around 5% maximum.
That's right. Well, so yes, that's right. So that is, as you're pointing out, a relatively small effect. It could probably be increased quite a bit if I was computationally able to look at much smaller filament thicknesses and much larger helical radii. So I was able to go to a reasonably large amplitude. I was able to go to the regime of geometry where those spirochetes that I showed in the beginning, Leptospira and Bergdorf-Ferry, live. But your point is well taken. That is a relatively minor effect. Nevertheless, I think.
But nevertheless, I mean, because I like the work very much, can you, because you now have this model for this polymeric solution, did you learn, or can you learn something from it where you have to tune your polymeric solution that you can increase?
One of the certainly possible future directions is optimization, looking at, I mean, we've certainly explored some of the parameters here, physical parameters, but certainly as you know, one of the things that I showed was that the solvent to total viscosity ratio was important as an amplifying effect in certain regimes. So that's one possibility. Also, what I'd like to do next is to look at the more general objective time derivative, the Gordon-Showalter derivative, because this introduces things like shear thinning. And I think that in real biological fluids, I don't, from my understanding is that it's really just not a safe assumption to say that it's purely viscoelastic. You're always going to have some shear thinning in terms of the viscoelasticity. This is what I've been told by the experimentalists.
So you did an infinite helix.
Yes.
Beautiful transformation you could use
Right.
to simplify the problem. But what if you have, say, a semi-infinite helix? Can you estimate the domain of influence of end effects?
I could estimate it. I am definitely resting on the experimental evidence that indicated that after you have 2 or 3 wavelengths, more or less the observations were not changed. But in general, I'm not sure I could do better than hand-waving argument. I mean, I could break something down, but I'd have no idea how accurate it actually was unless I computed using a completely different numerical method.
Okay.
The increase in amplitude as you go to the tail in the spermatozoa is associated with faster swimming in Newtonian fluids, and then you had that evidence from earlier computations for finite. I mean, how important do you think that the interaction between variation of amplitude and non-Newtonian effects could be?
Well,
Have you any sort of insight? I mean,
here's one thought. Value it how you will. With this finite body of increasing amplitude towards the tail, the consequences of viscoelasticity being complex, generally, if we think about one thing, which is that when they did the computations without an increasing amplitude, they found that it did not swim faster. You can think about the increasing amplitude as maybe hand-wavingly a linear combination of a periodic wave and maybe a flapping. Right? So if we add the two together, maybe we get some kind of increasing amplitude periodic wave. And the important fact there is that if I just have a flapping appendage in a Newtonian fluid, nothing happens by time reversibility, or scallop theorem, as you will. And so, but you do have pumping in a viscoelastic fluid. So at least that to me is evidence that the increasing amplitude is related to maybe just thinking about a flapping plate in a viscoelastic fluid. Thought.
I think we can continue this discussion over coffee, so thanks for speakers again, and we reconvene at 11.